Good afternoon, good evening, good night if I don't see you, right? Welcome, this is the MPI track 2. I hope you're in the right place. If not, I'm not offended if you decide to go upstairs, that's okay too. Yeah, so a little bit of an intro, let's see if this works. Yes, okay, so there's me. Oh my God. Disaster struck already. Okay, yes, all right. If I go back, does that work? Oh, it does work, wow. I got a brand new laptop and I'm so excited for it. And this little pen thing actually works. So, I'm Andrew, your instructor for MPI. I'm a research scientist at the School of Computing at the University of Wyoming. This is my second time teaching the MPI track. I taught last year. But what happened was I wasn't supposed to be the teacher last year. The teacher flew from the UK, from EPCC. Flew from EPCC last year to Newark, got stuck, and literally we had to find a replacement, which I volunteered. And then it turned out he didn't have any slides ready the night before, so I spent the whole 2 nights in a row, all night, making new slides. But at least this year I had time to make my own slides, so that's nice. So. Yeah, so just to give you part of the team, the cast, hands-on helpers, Ilio's the first hands-on helper. You'll see him around. I don't know, he should be here. Oh, here he is. Raise your hand if you're around. John Kaz is right there. Okay, that's what John looks like. He'll be at the back of the room. We even have Erwin, but he's not on my slide, so. Okay. We have Samir. Oh my God, this is a struggle. Okay, we're giving up. Okay, Samir is here to help. And we have Ramses, who's session chairing. Then we have, let's see here. Matthias Brust, he'll be doing the session chair tomorrow. We have Julie, who's doing the evaluation committee. Is James here, James Willis? He's in the back. He got added to the list, so I don't have a picture for him, but I'll add you later. So James is also going to be hands-on helping with the exercises, okay? A lot of this content is inspired by the other instructor who helped me out a lot last year, and David Henty, who's the actual original MPI instructor who could not make it. But a lot of that work comes from them. Now, track motivation. So I'm going to use a lot of this, my background in computational fluid dynamics to inspire the, parallel computing challenges and the techniques that I used in order to get performance and scalability up to over 1 million MPI ranks, right? On some interesting fluid flows, for example. So a lot of the applications that I saw from the poster sessions is related to stuff that have mesh-based applications, right? So in the top, you're looking at the front of an aircraft, right, with what's called an adaptive mesh. But in the principle of it is that in these, for fluid flows with meshes, your neighbors have to talk to each other, right? So the fluid flow going from the left room is going to pass through one cell, and I need to talk to my neighbors, right? So that's what I'm kind of talking about here. And so from CFD, right, we're really interested in what are the dynamics at the small scales all the way up to the large scales. So here you can see we did a really large simulation. This one is on 20,000 CPU cores, right? But we're tracking the turbulent wakes coming off of aircraft wings, right? But what's interesting about this is on the bottom left, you can kind of see the grid. It actually is changing in space, right? So this is H, adaptive mesh refinement, but we do it dynamically. We do it live. It's actually changing as the flow is changing. So we're moving resolution to where it's important, right? So in order to capture the dynamics, so if you're looking at the top of the wing, you can see all the fun turbulence and tracking what does it hit. But at the same time, I also work on wind energy stuff, simulations where I actually resolve the blades as well, right? So again, here you can see in the dark green, kind of, sort of, adaptive mesh that is almost Cartesian. And then in the teal, right, this light blue, it's an unstructured mesh, right? So in these applications, how do we communicate to resolve the fun turbulence and the wakes of a wind turbine? Because these wakes, for example, end up hitting turbines behind it, and you lose energy production. As you can tell, I spend too much time on visualization. So if you don't know, I work for the University of Wyoming. And the University of Wyoming, the logo is actually the bucking horse on the bottom. So it looks like a horse, and it's called Steamboat, and then there's a cowboy on the bottom. So I made a floating offshore wind turbine platform out of gold bucking horses. So yeah. Okay, track overview. Why are you here? I hope for good reasons. So we're going to cover derived data types and operations, and how do we construct data. I'll go into this in detail. Section 2, we'll do Cartesian virtual topologies. And from there, I actually used some of this stuff when I was a graduate student, and then I actually, in the Section 2, we'll see, even with a Cartesian topology, I used it to scale to over 1 million MPI ranks on Argonne supercomputer, so it actually works, so that's good. Then third, we'll do graph virtual topology. So when we have these really unstructured meshes, like how can we build something that's useful for communicating efficiently with the least calls possible to the MPI library? Then finally, with these new virtual topologies that we have, doing collective calls with the neighborhoods around, right? So the neighbors talk to each other front and back, and then having the ability to take advantage of that. And lastly, which is not really MPI, but how do you actually take an unstructured graph or a mesh and actually assign it to its own ranks? So last year we got some feedback, great, you showed us all these graph topologies and stuff, but how do I actually use it, right? And so at the very end, I put in a Metis demo. So we can learn how to partition graphs, okay? Day one, we're going to cover the first two. So we have an hour, and then we're going to do a half hour of hands-on, and then take a break, and then we'll go on to the next section, another hour, another half hour on hands-on. Any questions so far? Okay. In principle, right, this track is meant to serve those who have seen MPI before, but you could coincidentally be in here and not know what distributed memory parallel computing is, right? But let's just refresh, right? So you have your program, right? You wrote your software, and in your program you have a few variables, X and Y, for example, and it has some more data in there. Now, what does MPI really do, right? So what is distributed memory parallel computing? Well, what it does is it takes a copy of your program, and it's going to duplicate it. In this case, it says NP4, so it's num processes at the top in the yellow. MPI run, it's a wrapper, and says I need to duplicate and run 4 processes, and run my app, which is my application with args, and then it's going to make 4 copies of my program to 4 ranks, in a sense, right? And so in distributed memory parallel computing, we have a copy of the program on each MPI rank, and they all have their own data, right? They all have their own set of data. So as you can see, right, in rank 0, right, in green, we have a copy of integers X and Y. But that is different from the copy in rank 1 in blue, or the other ones, where they also have variables X and Y, but it's different, right? It's their own set of data. Okay, so just to illustrate this, if we say, okay, set X equals 0, in general, in your program, right? Because everyone has the exact same copy, the same page, basically, running it, right? So they're processing. So every rank is going to see X equals 0. right? So here, obviously, on rank 0 in my amp, in the green, the value of x is 0, right? What do we think, what's rank 1 going to be? What is x? It's going to be 0, okay, right? Not super trivial, right? But now, as you can see, barely, this says if rank equals 0, right? It's checking a conditional. So if my rank ID is 0, it says set my value x equals 1. But also note, see on the far side, we see the same line of code on rank 1. But the value, right, on rank 0 is obviously going to set the value of x to 1. And on the rank 1, it's still going to be 0 because my flag says I am not rank 1 or rank 0, I am rank 1, so don't do that operation, right? So we're manipulating our own set of data. So that's the principle of distributed memory parallel computing. Any questions so far? Yes? Right, so, oh God. Let's hear it. John Kaz. When we actually make our own sets of MPI ranks, right? And where, like, how does the actual internals of MPI like launch and kind of set up and coordinate our own batches of data? I actually don't know the underpinnings of really how that works. I just look at it as a, a memory like model, a thought process of how it actually works. The question, yes. Yeah. So the take-home message is the MPI implementation, when you run MPI run and the implementation of MPI, it does that under the hood and you don't need to worry about it. Okay? But if you go print the address, where does this value of x live, and you actually look at the physical address, it'll be different from this copy. But the MPI library takes care of that, and you do not need to worry about it, nor you should, right? So eventually, right, you could have an MPI rank on 2 different nodes, right? So they physically do not share the same actual DIMMs, RAM DIMMs, right? The actual physical hardware. But if you're on the same, right, like on your desktop or your laptop, you're working on the same physical, but the MPI library does that distribution for you, and you don't have to worry about it. If that makes sense. Sorry. Long-winded, good question. Pointless. Okay, now, again, they both see the same pieces, right? It's a physical copy, almost like I visualize it as a physical copy, right? I printed out my code. I said, okay, rank 0, you get a copy. Rank 1, you get a copy of the code, right? So they see the exact same lines of code, but all you have is a rank ID to differentiate yourself, right? So in the first one, it says if rank equals 0, do an MPI send a variable x, and to here, to rank 1, as what I'm indicating here. It's not the full function call, but. And then if you're rank 1, expect to receive and store it into a variable x, and expect to receive it from rank ID 0, right? And so in principle, the value is we're going to take our green x, right, which had a value of 1, and ship it over to rank 1, right? And through this process, then we end up giving a copy over, and right, so we're just communicating between in a distributed memory. That's how we pass information, right? So we have send receives in this thing, right? So in a send call at the top, we need to pass the address of what data we're going to send. We need to know how many of the things we're going to send. What is the type that we're going to send? Which rank it's going to go to. And if you're sending a whole bunch of these messages, you need to be able to figure out, like, oh, which message was it, right? Did I mean to send, the message A and receive message A and message B? And how do you differentiate? So you add a tag. And then inside this thing, right, you're going to have a communicator, which indicates your rank, right? Like I'm communicating with who, in a sense, right? So similarly with receive, where you're going to receive data into a memory buffer, it's just at the starting point of an address. How many, the data type again, which rank am I going to receive this information from? A matching tag from the send, communicator, and status, like if it got sent, right? So what's important here is you should already know from being experienced with MPI a little bit that you have to indicate the type, okay? So MPI gives you a whole bunch of intrinsic types, right? So in C and C++, you can send, like, for example, MPI int, or in Fortran, MPI integers, right? These are built-in data types, okay? But, what happens, in a sense, is we just need to know what is the starting point of the data we want to send, right? And so from here, right, we're just telling it where sbuf is, like the literally address of where the data begins that you want to send or receive into that memory location, right, starting. But what happens if we really want to send custom data that is not like an MPI integer or a double or a character or any of those listed, right? And so in your application, you maybe want to send like vectors, but you don't want to make a copy of your custom data into its own little buffer that is of type like doubles. So how do we actually get around without making copies, right? And so MPI was like clever enough to say, all right, let's give the developers the opportunity to build their own types. So that's really the motivation for derived data types. And then associated with your custom type, how do we do operations on it? How do I make a custom op, right? All right, so out of the ones we're going to talk about, we're going to look at contiguous. So really, you can see in the green blocks, they're back to back, right? So it makes sense, contiguous. They're touching in memory. Vector. So a vector would be like block, gap, with regular intervals, right? So there's little gaps. Indexed, you have data. So you have over on the right-hand side, blue. We have some irregularly spaced memory, right? We want to send the blue blocks, right? So it looks like we have 2 blue blocks, a space, 1 blue block. That's so hard to say. And then 3 gaps, and then another block of 2, right? And so how do we do that? And then finally, we could have some really crazy stuff, like if you're doing in C programming a struct, right? So for example, I could have a molecular dynamics code where I want to send particles, for example, that have a velocity, a mass, and attached to it, it has a particle ID, it's stored in an integer. So you're mixing a bunch of different intrinsic types, right? Like double precisions or floats, to integers, and you could have characters, right? And so how do we actually package this all up in order to send a single function call to MPI send, right? We got to make these types. We got to tell MPI how this works. Okay, so formally I would go through this, right? MPI contiguous, literally contiguous, right? Just to formalize it. So vector, regularly spaced. Create H vector. It's basically the same as vector, except for with the gaps. Instead of telling it the spaces in terms of the type, tell it in terms of bytes, which is a kind of a pain, but we'll look at it a little bit. Indexed, again, variable space, as we talked about. Create index block. This is really just a special case of the previous one. Subarrays, D-arrays, and then finally structs. But those subarrays and D-arrays, if you're so curious, there's going to be some of that in the parallel I/O session on Wednesday, as far as John knows. So it's really important for parallel I/O in the MPI library, so that's why I kind of defer on that point. Okay, so let's look at the actual MPI type contiguous. So here we have 3 parameters, right? We need to say how many we're going to send. what is the original type? Is it like a double or a float or an int? And then we're going to make a new handle, right, to say this is my new type. And that's what's in gold, the new type, okay? So really just the number of entries, how many, and the new type handle, right? So let's look at an example. This is like a little 2D array, a 4x4, statically allocated, okay? So that way it's contiguous in memory. So as you propagate along, starting at the top left from 1 to 4, right? Then immediately in memory at spacing, like the number 5 is actually right after 4, okay? So if we look at this MPI row type, that's what we're going to call our type. We're going to, if we want to send, for example, the green row, right? It's all contiguous in memory. Well, how many do we need to send? Well, the count, we're going to send one of our new row type, and then a destination like where is it going and a tag associated. But how do we actually build our type contiguous, our actual type? Well, we're going to send 4 things. What's next? Old type. What is the type? You guys know what type it's going to be? What's the old type of the data we're going to send? Yes. Float, right? So on the top left by the A, right, so A44, it says float. So when you tell MPI, it's an MPI float, right? And then finally, we put in our row type, right, that we can store it there. Now, right, if we come back down, and then finally, once you make it, you have to commit it. You have to tell MPI, I made a new type, register it, process it. You know, when you actually run it through the compiler, it's, oh, I know what a row type is. And then down below, we can see an example, right? That's how we actually use it. We're going to send one row type, which has 4 floats in it. Any questions? So far, so easy? OK, MPI vector. This is fast. How do we actually, if we have a grid of elements, how do we actually send like that internal like purple cells? Well, in memory, right, the memory itself is laid out, right? If we take a 2D array and we map it to a 1D vector, like how it maps out into memory itself, you can see how they butt up to each other contiguously in a sense, right? So you can imagine this is the memory array, like, you know, when you read in a cache line, for example. Now, when we look at these, we see, okay, we have gaps, and then we have 3 elements, then we have a gap of 2, and then we have 3 elements again, right? So remember with type vector, block, gap, okay? So to make a type vector, we need to know how many blocks, and to me, I ask, how many chunks of data do I have on the bottom? I have 2 chunks of data, right, that are touching. That's how you count, right? Next, you have to tell it what's called the block lengths. So how many elements inside of each chunk do I have, right? How many things in a chunk? I have 3 things in a chunk, okay? Stride. So stride is the number of elements between the start of each block. Well, that's 5, right? So I start at the very beginning, and then how many steps do I need to take in terms of the old type to get to the next chunk, right? So that's 5, okay? Then we're going to pass in, for example, again, an old data type, and then we're going to get our new handle, right? New type, and that's how we construct it. Okay, now, that's really boring, right, with simple things, but you can actually start doing much more complicated things where you can take a type contiguous, or for example, we can take structs, right? We have structs. This looks like block, right? A block of data, and a gap, right? So we can actually hierarchically build block, gap. And that's where the powerful power of these derived data types can get you, right? So you can start to construct more complicated things. But as a simple example again, we have a Cartesian array chunk. And the size of this chunk of data we have on our process is going to be bx plus 2 by by plus 2. But the data in green is of length, you know, bx along the top. So we have bx elements, right? Some some number, and then we have by, we can change the size of this. And then if we just want to send this vector, right? And if you remember, we took, like on that previous example, and we lined it out. What is, how many items are we going to send, right? So if we look back here, it looks like we have block, a giant gap that loops all the way back around, block, gap, and it's all the same, right? The same block size as 1. We're going to send by of these things, right? We have by chunks of data, each of size 1. And then the stride of this thing, or the block length, we just have one of these green elements per chunk of data. And then we have our stride, which is going to loop all the way back around. And how many is that? It's going to be bx plus 2. And then we have our old data type and our new data type. And then again, you can do more complicated things where I guess I skipped already to the next slide. This is h vector. But if I go back, right? So that's how you see the power of vectors, right? But again, it gets more complicated later on if you have complicated data. But you can use this for regular like finite difference methods, for example, if you're in numerical partial differential equations. Okay. Next, create h vector, which is similar to vector, but it uses byte spacing instead of the old how many old types am I marching. Okay. Similar, how many blocks, how many number of elements in the blocks, how many bytes between each block. Old type, new type. So similar. They all look the same, right? Basically. They just get a few more parameters as you go. But here in this example, you can see the stride is set into 11 bytes, right? But it'll look like block, gap, but now we just need to be careful with what the offsets are with the bytes. Okay, so a similar example. Again, we're going to send by things. I guess I should have colored that green, but that's all right. We're going to send by count of elements, and each chunk has one element. And then to loop all the way back around with a stride, again, it's bx plus 2. Okay. Getting a little more complex. Indexed. Okay. So now, with index, we're going to have, that's not a very useful description, length of array of displacements. But it's, again, how many chunks of data, how many green things do we have that are in this, right? So if we start from the bottom left, we have 1, 2, 3, 4, 5, 6. Chunks of green. Okay? The array of block lengths. So in each one of those chunks, you have to indicate how many of the old types you have, right? So in the first one, we have 1. So we have this array of here, I think I did 6 things. I think we'll see on the next one. Let me skip over that. Right? So we had 6 green chunks of data. And then we have an array of block lengths, 6, kind of hard, but we have, and you put the counts in it. How many of each one of these chunks are they, right? So 1, 1, 2, 1, 2, 1. Then the displacements is telling you where it starts, right? So with each chunk, so the very first chunk is going to start index 0, and then it's going to start at index 3 for the second chunk, 5, 9, 13, and 17. Right? And the type again, and how do we store it? Okay, we're almost through these crazy types, right? Create index block. This is basically a special case of the previous one. So the last one was more generic, but again, you basically count the number of chunks and the bytes between them, and et cetera, right? So this one, how many chunks do we have? We have 5. The block length, we're going to have 2. Let's see here. That's the size of the blocks, right? So each block is of size 2, right? So it's really just a custom, but then in the displacements, we have to tell how each one of these blocks of 2s are set. So, and then you see at the top, it starts at 0, 5, 8, 13, and 18. Okay, tell the old type and store it again. Okay, structs. This is the fun part, right? So you guys have particles. Does anyone have a crazy struct in their application? Let me ask this. what are your research areas, like the stuff you're simulating? Anyone? Yes. Particle in cells. Okay, particle and cell symbols. So particles, right? And so what do you store? Do you store your data into like custom data types like a struct? Okay, in one version. And the other one is probably like packed like integers and doubles, right? And stuff like that. So, but if you don't want to like destroy your code base because you already wrote a struct with a particle, for example, or like down here in this data struct example, where I have an ID, a flag, which is a character size, and two floats, X and Y, right? I don't really like want to rewrite my entire code to have, let me store all IDs into one vector for every single particle. Then let me store every single flag into a vector of characters, and then another, vector of floats with X and then Ys, right? So is there a convenient way? Of course there is, right? So again, similar, how many blocks in a struct, right? So down here we have 2, and then we have to say how many objects are in each of these entries. So here in like int, we have one int shown in blue, and then we have one flag which could be shown in the white in between the blue and the green, and then we have 2 floats, for example, right? So the array of block lengths would be 1, 1, 2, right? And then displacements, because structs are crazy, we have to use bytes. And then you'll see it even gets nastier soon on how do we actually keep track of all these bytes. But yes. And then you have to tell all the types, right? We just packed integers with characters, with floats, with, and then we could even pack like contiguous types that we made or previous vectors, right? Because it could be hierarchical. Okay. So let's look at a real particle. Yes? Yes, I will get to that. But yeah, to your point, how would we do this otherwise? We would either make copies of the same type to use like, oh, I'm going to send MPI floats, right? So that means, oh, I better allocate a new array, right, of just floats and then pack them all in there and then do an MPI send of MPI float type, right? And then you have to unpack it and put it back all in, right? Or you could just send a whole bunch of messages, right? MPI send this one, this float, this float, this float, and just send a whole bunch of messages. But it turns out with calling the MPI library, the overhead of actually making an MPI send call in terms of like cost, in terms of wall clock time, is actually the expensive part rather than the actual communication for a small thing. So for example, if I send one float, but I need to send 2 floats, if I send 2 messages of size 1, it'll take twice as long than if I just sent one message with 2 floats. So I want to reduce the number of calls that I can to the MPI library. Does that make sense? Okay. Yes? Yes. Exactly. Yes. Yeah. 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 So in the way beginning, right? It looks like MPI. It would look just like sending like MPI doubles, right? A vector or whatever, right? Because it's contiguous, the same type, all packed together, right? But it could be that you actually built, for example, down here, we're going to build a bunch of structs, right? I'm trying to, in a sense, when you have the hierarchical construction of it, I'm trying to think about the offsets. Yes, John Kaz. Yeah, so like index, for example, from my own like research, we end up packing variable amounts of data where like, okay, my rank needs to send what are called donors and receptors in a sense. It's basically like when I have overlapping cells, right? We have those multiple meshes, right? The green mesh and the teal mesh, okay? And they need to actually, when they overlap each other, we exchange data. But in this process of who needs to send to who, we actually get variable amounts of like kind of these weird structs, but the offsets are really kind of random almost. And so we get these complicated things, but to make the MPI call simpler, to reduce the number of MPI calls, right, then index can come into play. You'll see actually in the hands-on demo, we have a very simple case of it. Then you can see how to construct it. I don't know it is as complex as you'd like to see, but I can take a look to see if I can find a more advanced example, for example. Any other questions so far? Okay. All right, structs, we need those byte offsets, right? And so how do we actually find, right? So in order to do structs, we have, for example, right, like down here, we have 4 floats and then 2 integers, for example. But we could have crazy stuff in there like characters. So characters have 1 byte each, right? In order to register this type, right, with MPI, we need to tell the byte offsets, right? So like, okay, if it was an integer, 4 bytes, and then we have a character, which is 1 byte, so the offset would be 4, and then after that would be another one, 5 for the data that comes after characters, right? So you have to tell the bytes. But what happens is you need to be very careful with addressing and MPI. And so it turns out like what we can do is we can ask, there's a function called MPI type extent, and you say, how big is an MPI float? And it'll say, oh, it's 4 bytes, right? You assume it's 4 bytes because you've been programming. And so down here in this example, you can say, okay, the first offset of where do the floats start? It starts at 0 index, right? But how many bytes, where does the int start? You'd assume it's 4 times the size of an MPI float. But actually, do you know why we can get into trouble? Why that's not safe? I know it's a little advanced. Okay, let's take this example. So we have a character A, 1 byte, and then we have an integer, which is 4 bytes, and then another character, and we have this struct called x. But it turns out the compiler says, I need to get performance, right? And so it aligns on 4 byte boundaries, for example. So what can happen is the compiler can go add random crap into your struct. And so you don't see this when you actually program it, but what happens is the compiler adds 2 gap arrays and handles the things on the underside of your code. So if you asked for the extents of like, oh, I have 1 character size, right? I know it's 1 byte, the offset should be 1. But it turns out it added, right, 3 more characters in order to fit like a 4 byte boundary. So your offsets could be wrong, and you could be programming your function incorrect. Okay, so how do we actually handle this? One way is to use this getAddress function. So you do is you store bases, and then it turns out this even fails, which is terrible, because at the very end of each one of your structs, it can add more padding. But all right, so let's actually figure this out. What you do is have this, first you construct your type, your struct, okay? You say, okay, give me the first address, and then you say, okay, great, I'm gonna pass in particle x, and I'm gonna store it into it's called f offset in the second line. Great, get the third address, where do the integers start, right? So I'm getting base, which would be the beginning of the particle. And then I get the address of where x starts, right? So in theory, hopefully it's 0. And then I jump to the next type and say, where does n start? So that's why we see particle, particle.x, and particle.n to see where the floats offset and where the integers offset, right? But at the very end of this thing, again, the compiler can add data after, which can get you in trouble when you want to pack a bunch of particles together. So instead of particles, there could be some extra data right here, and then another particle, some extra data that you didn't account for, and again. So what do? You make this whole new type. Then what you do, you check, is it actually the correct size? And if it's not, we have to resize this struct. Okay. So resize, input your old data type, tell it the lower bound, the extent in bytes, and then the new type.